Tiny particles dictate the shape of the universe in ways you've never imagined, and the hidden ties between the quantum realm and colossal cosmic structures will blow your mind. Stay tuned, because number 1 reveals a mystery almost nobody predicts. Quantum fluctuations, those fleeting blips of energy in the vacuum, may have sown the first seeds of galaxies. During cosmic inflation, space expanded faster than light, stretching these minuscule variations into density differences that later attracted matter. Over billions of years, the slightly denser regions gathered gas, forming the first star-filled islands that grew into the sprawling galaxies we observe today. Researchers estimate that without this quantum jitter, the universe would be a featureless expanse. This link illustrates how the tiniest uncertainty can dictate the grandest structures. Up next, we'll see how the invisible hand of dark matter shapes the spin of entire galaxies.
Surprisingly, the unseen particles we call dark matter act like a cosmic scaffolding, governing how galaxies rotate. Observations of spiral galaxies show that stars at the edges move far faster than visible matter alone would allow, implying an extra mass halo surrounding each galaxy. Simulations suggest that weakly interacting massive particles, or other exotic candidates, form this halo, providing the gravitational glue that prevents galaxies from tearing apart. By influencing the distribution of ordinary matter, dark matter indirectly guides the formation of spiral arms, and even the clustering of galaxy groups. While its exact nature remains elusive, the consensus among astrophysicists is that dark matter is essential for the large-scale architecture of the cosmos. Later, we'll explore how the afterglow of the Big Bang records those primordial ripples.
In the faint afterglow of the Big Bang, the cosmic microwave background carries a subtle pattern that mirrors the universe's earliest quantum ripples. When the universe cooled enough for photons to travel freely, around 380,000 years after the initial explosion, the temperature variations captured in the CMB were directly imprinted by the inflation-amplified quantum fluctuations. These minute-hot and cold spots, only a few microkelvins apart, correspond to regions that later evolved into galaxy clusters and voids. By mapping the CMB with satellites like Planck, scientists have traced a bridge from subatomic uncertainty to the vast cosmic web. This connection proves that the seeds of massive structures were sown in the quantum foam itself. Next, the ghostly neutrinos from exploding stars will show their subtle influence.
Few people know that the nearly massless neutrinos streaming from supernovae play a quiet yet significant role in sculpting the universe's large-scale structure. Each massive star's death releases an enormous burst of neutrinos, carrying away about 99% of the explosion's energy. Though they interact weakly, the sheer number of these particles contributes to the overall energy density of the cosmos, affecting the rate of expansion. Over cosmic time, the collective background of relic neutrinos, left over from the early universe, damps the growth of small-scale structures, subtly smoothing the distribution of galaxies. This effect, while modest, is accounted for in precision cosmology models that aim to match observations of the cosmic web. Soon we'll dive into how spacetime itself vibrates in gravitational waves.
Hidden within the fabric of spacetime are ripples that echo the quantum nature of the universe. Gravitational waves, first directly detected in 2015, arise from cataclysmic events like black hole mergers, where extreme curvature produces disturbances that propagate at light speed. Some theoretical frameworks suggest these waves carry signatures of quantum gravity, offering a rare glimpse into the Planck scale regime where general relativity and quantum mechanics converge. While direct evidence of quantum imprints remains speculative, the very existence of these waves confirms that massive objects can communicate across vast distances through spacetime itself, linking the colossal to the minute. After that, the Higgs field's role in star birth takes center stage.
Deep beneath the particle zoo lies the Higgs field, an omnipresent energy that endows elementary particles with mass. Without this mechanism, quarks and electrons would zip around at light speed, unable to clump together under gravity. The acquisition of mass allows protons and neutrons to form atomic nuclei, which then combine into hydrogen and helium, the raw material for stars. In the cores of nascent galaxies, these atoms collapse under gravity, igniting nuclear fusion and lighting up the universe. Thus, the Higgs field, a quantum entity, directly underpins the existence of the luminous giants that dominate the night sky. Coming up, we'll discuss a speculative process that could end the universe.
Remarkably, some grand unified theories predict that protons, the building blocks of ordinary matter, are not eternal but can decay over astronomically long time scales. If proton decay occurs, it would gradually erode matter, converting it into lighter particles and radiation. Current experiments have placed lower bounds on the proton's half-life at around 10 to the power of 34 years, far exceeding the current age of the universe. Should decay happen, it would serve as a cosmic clock, ultimately leading to a universe where only radiation remains. While no definitive observation exists yet, the possibility reshapes our understanding of the universe's ultimate fate, linking subatomic instability to the grand timeline of cosmic evolution. Next, we'll revisit the primordial soup recreated in particle colliders.
Consider the searing fireball produced when heavy ions collide at near light speed in modern accelerators. In these fleeting moments, quarks and gluons break free from their usual confinement, forming a quark-gluon plasma, a state of matter that dominated the universe microseconds after the Big Bang. By studying this plasma, physicists can infer the conditions that existed when the cosmos was a hot, dense broth, before protons and neutrons coalesced. Measurements of temperature, viscosity, and flow patterns in the plasma reveal how the early universe expanded and cooled, setting the stage for galaxy formation. This laboratory recreation bridges the gap between particle physics and cosmology, allowing us to test theories about the universe's infancy. Then we'll examine a surprising entanglement that stretches across billions of light years.
Scientists have recently measured entangled photon pairs that originated from quasars billions of light years apart, confirming that quantum correlations can persist across cosmic scales. By selecting light from distant astronomical sources to set measurement settings, researchers closed loopholes that previously challenged Bell test experiments. The results suggest that the spooky action at a distance described by Einstein is not limited to laboratory distances but is a fundamental feature of reality, potentially influencing how information propagates throughout the universe. This finding hints that quantum mechanics may play a subtle role in the large-scale coherence of the cosmos, though the exact implications remain under exploration. Finally, we'll confront the deepest puzzle linking the tiniest scale to the universe's expansion.
Finally, the most profound connection lies in the tension between the Planck scale, the realm where quantum gravity reigns, and the cosmological constant that drives the universe's accelerated expansion. Quantum field theory predicts a vacuum energy density many orders of magnitude larger than what astronomers observe as dark energy. This discrepancy, often called the worst prediction in physics, suggests that our understanding of how tiny quantum fluctuations translate into the large-scale dynamics of spacetime is incomplete. Researchers propose various resolutions, from new symmetries to multiverse ideas, each attempting to reconcile the minuscule with the massive. Solving this puzzle could unlock a unified description of nature, bridging the gap between the smallest particles and the grandest cosmic structures.
We've traveled from the jittery quantum foam that sparked the first galaxies all the way to the profound mystery of why the vacuum energy is so small, uncovering how the tiniest constituents whisper to the vastest realms. If you enjoyed this journey, hit the like button and subscribe so you don't miss the next mind-blowing list that arrives every week. Which connection surprised you most? Tell me in the comments below. Thanks for watching, and keep looking up at the stars while remembering the particles dancing beneath them.